As we discussed in the Why Not Only CTLE video, one reason is the design trade-offs between the peaking gain and bandwidth. But we haven't dived into the circuit block, and we got lots of feedback asking why there is a peaking gain and bandwidth trade-off in CTLE. Let me spend a short amount of time telling you why. Before understanding the design trade-offs in detail, we should look at what circuit block option we could have. From the frequency response, the channel is a narrowband low-pass response, which creates the intersymbol interference ISI issue. Therefore, to mitigate the ISI by equalizing the frequency response to a wide bandwidth, we could put a high-pass filter at the channel output, which is the CTLE in the RX. From the Electronic 101, we know the filter can be a passive filter or an active filter. Which one do you think we should have? Correct. Having the active filter to provide a gain at the next rate may increase the RX input sensitivity, even though the passive filter is more linear than the active filter with less distortion. If we decide on the active filter for the CTLE circuit block, the most robust and simplest topology would be a differential mode common source amplifier, which is a kernel logic CML amplifier. But how to implement the high-pass filter in the CML amplifier? Think about the gain amplitude for 5 seconds. Bingo! We know the gain of the amplifier is GMR, which is transconductance of the transistor times the rho. But neither the GM nor the R is a high-pass response. Let's start with how we could implement the frequency-dependent gain. Again, since we need to generate the frequency-dependent gain, we can apply the frequency-dependent law instead of the resistive law. Do you have any idea which component can provide high impedance at a high frequency but low impedance at a low frequency? Think about the passive images for 5 seconds. Correct. That's the inductor. But you might need 2 inductors in one CTLE stage, and then how many stages we will decide to multiply it. So the floor plan of the CTLE image would be something to look at this. The most obvious one is the area penalty, which is very expensive, especially in 3nm FinFET. Those advanced processes. Anything else from the area issue? Right. To mitigate the area penalty, we could squeeze all the inductors together to minimize the area. But the design complexity of handling those inductors coupling in the electromagnetic EM modeling and big multiple S-parameter transient simulation would be tremendous. If we miss any design consideration here, the whole CTLE would fail the response you would like to achieve. Anything else could be the issue. Think about the linear phase images for 5 seconds. Yep, one more design pitfall is that you can design and handle the AC magnetic response well with those inductors. We might overlook the phase response, which was now constant group delay and no longer to be a linear phase. This is a soft reminder for all CTLE designers. We are likely to realize the same issue as the paper mentioned, spending lots of time to optimize the AC response without looking at the I diagram at all and finding the I width is bad after a few weeks of design time. So even though time domain simulation is time consuming. It's necessary to check it as soon as possible. If the inductor law may have the linearity issue and cannot tune the peaking gain easily, can we have other options to achieve the CTLE's required frequency response easy in a more linear response? Yes, we have another choice to apply the frequency-dependent transconductance of the transistors. We've known the source degeneration resistors Is can provide negative feedback to stabilize the DC operating point and reduce the DC gain, but keep the highest available high frequency gain by an AC sorted capacitance CS. Thanks to the source degeneration, the CTLE has a better linearity and a flattened frequency response without ring. Also, the area overhead at the source degeneration is not that serious and provides us with a better pole zero response tuning and less design complexity. Let's dive into the source degeneration CTLE topology. As you can see, the RD12 is the resistive load, and the CP will be the passive associated with the device capacitance. The Is CS of the input differential pair M1, M2 sets the pole and zero of the frequency response. Before diving into the equation, let's intuitively look at the frequency response. At DC or very low frequency, the CS is open, and the parallel RC network is dominated by the RS, so the DC gain drops. On the other hand, at a higher frequency, the RS impedance is much larger than the 1 over omega CS, so the parallel RC network is dominated by the CS, and the gain is higher to achieve the high pass characteristic. Of course, due to the output pole determined by the RDCP, and the bandwidth is dominated by the RC time constant. You can try to derive the first order equation without considering the RO of those transistors, and then put it into the Python code to do a ballpark design exercise. Another intuitive way of looking at the equation in the time domain is to apply a long run and 1010 pattern after loss channel to a CTLE. As you can see, the long run static 100 swing got attenuated, while the 1010 clock pattern swing is amplified. Then both pattern swing are equalized. In reality, the second order finite output impedance RO of the transistor and the low supply may degrade the gain at the next rate lower than what you need. The straightforward topology is to cascade more CTLE stages instead of a single stage to buy you more voltage gain at the next rate to provide a higher input sensitivity over RX for the system link budget. However, nothing comes for free. There are lots of design trade-offs associated with the peaking gain or the gain at the next rate or number of stages, such as bandwidth, SNR, response tunability, power, linearity, linear phase, design layout complexity. To narrow down the design trade-off between the peaking gain and bandwidth, we can show a quick ballpark bandwidth estimation based on a simple example by fan-out of 1, which makes all the cascaded amplifiers all the same size. If there are two-stage CTLE plus the summing amplifier in DFE, the total number of stages will be 3, and the bandwidth of each stage is 12 GHz, then result in a 6 GHz total bandwidth, which would be good enough for the 12 gigabit per second usage and reasonable power, linearity, and design complexity. The total gain at the next rate could be 14 to 18 dB over PVT conditions. Of course, the maximum peaking gain between the DC gain and the gain at the next ray is limited to 15 dB to 20 dB over PVT. But that's good enough and probably more than what we need. Unfortunately, if we shift the design target to 25 gigabit per second or 32 gigabit per second, the total bandwidth is not wide enough. We may need to either decrease the stage of the amplifier or reduce the gain at the next ray to 8 dB such that the total CTLE bandwidth can be at least 16 GHz. I hope this CTLE design image provides you with some idea of how the peaking gain or even gains at the next ray and bandwidth trade-offs. Here are a summarized image of why there is a peaking gain and bandwidth trade-off in CTLE. To deal with a channel loss up to 30 dB at the next ray, the CTLE topology must be an active filter with voltage gain at high frequency, instead of the passive filter, even though the inductive low CM low would provide a wide bandwidth and peaking behavior. The tremendous area, design complexity, and pitfalls in the linearity may push us toward the source degeneration CTLE. Unfortunately, the resistive load has limited bandwidth. In addition, the finite output impedance RO of the transistor and the low supply may degrade the gain at the next ray lower than what we need. To improve the peaking gain or the gain at the next ray, we could cascade a few source degeneration CTLE stages, but the bandwidth shrink quickly even though with a fan-out of one arrangement. We could make another fine-tune to extend the bandwidth back by reducing the gain at the next ray, which may reduce the RX input sensitivity. Therefore, the limitation image of the peaking gain and bandwidth trade-off should be obvious to you, especially at a higher data rate target. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.